Good morning, everyone. Today we are going to derive the equations of equilibrium and polar or cylindrical coordinates for a three-dimensional system. In the last class, we had derived the equations of equilibrium and polar or cylindrical coordinates in a two-dimensional system. So the polar coordinates are r, theta, z. In terms of Cartesian, it is nothing but x, y, z. So I can write x is equal to r cos theta, y is equal to r sin theta. Or with this, I can also write r square is x square plus y square. Or angle theta is nothing but tan inverse of y divided by x. Okay. We are going to consider an asymmetric body, and the axis of the body is going to be taken as z axis, and the other two coordinates are going to be r and theta. So I'm going to consider a point P so that the rectangular stress components for that particular point are going to be derived. And the coordinates of the point P are going to be r, theta and z. First, let me just draw a three-dimensional figure. Later on, we can arrive at the equations. So this is y-axis and this is going to be x-axis. Okay, this is going to be in such a way. Now r lies in xy plane. This is where r is going to lie, and then an angle theta is going to be made with respect to r. So this is theta and this is d theta. Alright, so I can draw the cylinder in this way. So here we have our cylindrical component. That is under consideration. Alright, and then theta, d theta, till here from the origin the distance is going to be r, and this dimension is nothing but dr. Alright, and then this particular dimension is dz. Yes. Now let me just give the namings for the vertices. Let me call this as D, this as A, C and B. Similarly, here it is going to be B dash, C dash, A dash and then D dash. Here in this particular body, somewhere I'll be considering a point P. Say something like here, a point P of coordinates r, theta, z. So P has coordinates of r, theta, z. We are supposed to find the rectangular stress components of this particular point. And the rectangular stress components are nothing but sigma r, sigma theta, sigma z, tau theta r, tau theta z, and then tau z r. So these are rectangular stress components of the point P. Okay, sigma r, sigma theta, sigma z are nothing but radial, circumferential, and axial stresses respectively. All right. So we are going to consider a radial length of dr. I can even write this as delta r. I can even write this as delta z. Okay. And this can also be written as delta theta. In some textbooks you have d theta, in some textbooks you have delta theta. That is nothing to worry about. So whichever is that you are going to follow, d theta or delta theta, kindly stick to one with respect to all the others. Fine. Now, for the ease of writing the stresses on every single face, let me just blow it up into different pieces, because if I try to write everything over here, it will be very confusing and it will start to overlap. So what I'll do is I am just going to blow up or separate every single piece of the rectangular cylindrical component. So say this is going to be the top face. Okay, this is going to be the backside face, and then I have the bottom face, and I am going to have a front face. Here I will be having the side face, and then the behind side face. So we have 1, 2, 3, 4, 5, and 6 pieces or 6 faces. I'll just write the dimensions, the vertices A, B, C, D, and this is A, B, A dash, and then B dash. This is C, B, B dash, and then C dash. This front is D, D dash, C, C dash. The bottom face is A dash, B dash, C dash, D dash. And this side is D, D dash, and then A, A dash. This is done only for the ease of understanding. This need not be done in your exams. Directly, you can just mention all the stresses over here itself. Okay. For every single face, I'll be using different colors so that you can identify what is the stress that is going to be there on every face. Now, starting off with the top face, that is A, B, C, D, we are going to have sigma z dash stress, and then tau zr stress, and then tau z theta dash. Okay, and for I'll just write down for the bottom because these are the ones that are exactly opposite. So here we have positive sigma z dash. This is sigma z negative. In this direction, I have sigma zr. So I have to write it in the opposite direction, sigma zr. This direction is sigma z theta dash. So in this direction, it is sigma z theta. All right. Now let us write for the side face. To begin off with the side face, it is going to be C, B, C dash, B dash. The opposite faces A, D, D dash, and then followed by A dash. So for these two particular faces, the first it is going to be sigma R dash, tau RZ dash, and then tau R theta dash. Exactly here, I will be writing the opposite. This is the direction for positive sigma r. So this is going to be sigma r. This is sigma r dash and then sigma r. Upwards is tau r z dash. So downwards it is going to be tau r z. This is the direction for tau r theta dash. So the opposite tau r theta. Last, you have D, C, C dash, A dash, A, B, B dash, A dash. So this is going to be the phase where we are going to write the positive stresses. Alright, this is going to be the one where we are going to write the negative stresses. Alright, so do not get confused that this is the place where we are supposed to write the positive. But here there is just a slight difference that this is the place where we write the negative stresses. Fine. Let us write the stress value for A, B, B dash, A dash. So here it is going to be tau theta Z dash and then sigma theta dash and then tau r theta dash. So coming to this particular phase, the directions are going to be exactly opposite. Positive is tau theta Z dash. So here it is tau theta z. This is the direction for sigma theta. And then this shall be the direction for tau r theta. Alright, we have written all the forces, all the stresses, that are going to be created on this particular cylinder. Now, let us write the area for every single phase. We need to write down the areas without which we cannot calculate the stresses. So, to start off with the area, let us go phase by phase. For the first phase, that is A dash, D dash, D. I'm talking about A dash, D dash, D. So, area of phases A dash, D dash, D. It is R delta theta delta Z. Next, B dash, C dash, C. It is R plus delta R delta theta delta Z. Here to here it is R. When we come out to this particular phase, it is going to be plus delta R, this distance. Hence it is R plus delta R. Now coming to phase D, C, C dash, D dash, it is delta R delta Z. And for phase A, B, B dash, A dash, also it is delta R delta Z. We are talking about D, C, C dash, D dash. This phase, that is this particular phase, and then this particular phase. Here it is just with the distance of this particular angle of delta theta that we are writing. So the angle is going to be equal, that is the area is going to be equal, that is delta R and then delta Z. Coming to the phase of A, B, C, D. The area is going to be R plus delta R by 2 delta theta delta Z. Coming to phase A dash, B dash, C dash, D dash, also it is R plus delta R by 2 delta theta delta Z. This is these two. You have delta R by 2, delta R by 2. This is because the average stresses, on these phases are assumed to be acting at the midpoint, alright, of the top and bottom faces, right? We're talking about A, B, C, D, A dash, B dash, C dash, D dash. These two are the top and bottom faces. So exactly in the center, we'll be considering the stresses to act. So this particular distance is delta r. So half means it is going to be delta r by 2. Hence that is the value of area. Alright. Now coming to the next point, that is equating all the forces. We are going to consider, we had considered capital X, capital Y, capital Z as body forces. So consider sigma r, sigma theta, sigma z to be the component of body forces. Okay, and this is per unit volume. Alright, that was the reason why we had multiplied with volume in for the two-dimensional derivation that we had done in the previous class. Next, I am going to write summation of all the forces along the r direction to be 0. I'll be considering the equilibrium of all the forces about r direction to be equal to 0. So it is going to be sigma r plus dou sigma r by dou r into delta r plus delta r into delta theta delta z. Okay, before we come to this, let me write what is the value of sigma z dash, tau theta z dash, tau theta dash, tau r theta dash, and all those things. Okay, so I'll just write it over here. For every single phase, it is going to have its own normal stress and then tangential stress. Okay, so I'll just write it like this. Let this be the normal stress, and then let this be the tangential stress. Okay, so to begin with, A dash, D dash, D. The normal stress is sigma r. Tangential stress is tau r z, tau r theta. B dash, C dash, C. Normal stress is sigma r plus dou sigma r by dou r delta r. Tangential stresses are tau r z plus dou tau rz by dou r into delta r, and then tau r theta plus dou tau r theta by dou r into delta r. Alright, next coming to D, C, C dash, D. D dash, the normal stress is tau theta. Tangential are tau r theta, tau theta z. Next, A, B, B dash, A dash. Normal stress is sigma theta plus dou sigma theta divided by dou theta into delta theta. This is sigma theta. And then coming to tangential stress, it is tau r theta plus dou times tau r theta by dou theta into delta theta, and then it is tau theta z plus dou tau theta z divided by dou theta into delta theta. The last one, A, B, C, D, it is sigma z plus dou sigma z by dou z into delta z, and then here it is tau rz plus dou tau rz divided by dou z delta z, then tau theta z plus dou tau theta z by dou z delta z. Coming to A dash, B dash, C dash, D dash, the sigma z, tau r z, and then tau theta z. Alright, these are the value of forces. Now you can see that the denominator and then the component with which it is being multiplied is varying. Dou r, dou theta, dou z, delta z. That is because of the dimension of these phases. Okay, I'll just give you one example how. So consider this particular phase. Let us consider A, B, C, D. A dash, B dash, C dash, D dash. That is this A, B, C, D. A dash, B dash, C dash, D dash. What is the distance between them? Delta Z. So consider this here, rho Z, delta Z. Alright. Next, A, D, D dash, A dash, B, C, C dash, B dash. That is A, D, D dash, A dash, B, C, C dash, D dash. What is the distance between them? Delta R. See here, A, D, D dash, A dash, and then B, C, C dash, B dash, delta R. Coming to the other two, D, C, C dash, D dash, A, B, B dash, A dash. See here, D, C, C dash, D dash, A, B, B dash, A dash. It is with a distance of the angle, that is delta theta. So we have written by delta dou theta and then delta theta. This is how the value varies. This is how you get to know with respect to what the differentiation is going to be done. Alright. So let us continue here. I'm going to consider all the components along the R direction. Alright. So considering the components along R direction, I would be left with, I've written the first component. We are just taking up the values. We are just seeing the values that are going to be in the R direction from this diagram, and then I'm just writing it down. First one is sigma R plus dou sigma R by dou R into delta R into R plus delta R into dou theta, sorry, delta theta plus delta Z. Then plus we have tau Rz plus dou tau Rz by dou Z into delta Z into R plus delta R by 2 into delta theta delta R, followed by minus sigma R delta theta delta Z minus tau Rz times R plus delta R by 2 into delta theta delta R minus sigma theta sine of delta theta by 2 delta R delta Z minus tau R theta cos delta theta by 2 delta R delta Z minus sigma theta plus dou sigma theta by dou theta delta theta into sine of delta theta by 2 delta R delta Z plus tau R theta plus dou tau R theta by dou theta into delta theta cos delta theta by 2 delta R delta Z plus last one body force component. Okay. Now you people can see that we have used sine cos terms. This is because in the previous class we had done we had taken the resolution for sigma theta so that it lies on the x direction over there. So similarly, if you try to resolve it to take up the equilibrium of forces along r direction, you will be getting sine theta and then following cos theta also. Alright. So finally, if you simplify all of this, we will arrive at the equations of equilibrium. Alright. So if you open the brackets, multiply, ignore or neglect the higher order terms, consider cos of delta theta by 2 as delta theta by 2, sine of delta theta by 2 as delta theta by 2. As we done in the previous class, we are going to arrive at dou sigma r by dou r plus dou tau rz by dou z plus 1 by r dou tau r theta by dou theta plus sigma r minus sigma theta by r plus gamma r equals 0. This is the equation of equilibrium while you are considering summation of all the forces along r direction is 0 or summation fr is equal to 0. Similarly, if you consider summation f theta is equal to 0 and then summation fz is equal to 0, then you are going to get the other two equations, that is dou tau rz by dou r plus dou sigma z by dou z plus 1 by r dou tau theta z by dou theta plus tau rz by r plus gamma of z is equal to 0. Similarly, the last one is dou tau r theta by dou r plus dou tau theta z divided by dou z plus 1 divided by r dou sigma theta by dou theta plus 2 times tau r theta by r plus gamma theta equals 0. So we have equations of equilibrium over here. These are equations of equilibrium in polar or cylindrical coordinates. So only if you understand the 2 dimensions, you can understand the 3 dimensions. Alright.